Hi, I'm Scott Weiss, architect at Solo.io.
And I'm Eitan Yarmush. I'm also an architect at Solo.io.
And today we're going to discuss how to debug and observe a multi-cluster service graph. And we'll explain what that means. So from a high level, this talk is going to go over a problem statement in which we'll describe some of the trade-offs that happen in a multi-service, microservice architecture, and how this creates what we call a service graph as a concept that we can then expand and understand how in a Kubernetes environment, the service graph is represented, how service mesh then plays into that. And then in a multi-cluster environment, when you have many moving pieces, how do we grok it? How do we understand this? Finally, we'll show an overview about observability and the tools that service mesh gives us to actually understand this and how we bring it together in a multi-mesh environment. So let's start with the problem. We have this problem that we see everywhere in the Kubernetes ecosystem today, and in general in the movement to cloud, which is the movement from monolithic architectures and applications to microservice architectures. You're all probably very tired of hearing about this digital transformation by now, but the point that we want to highlight here is how hard it actually becomes to observe what's going on in the system. When you have everything running in one application, it's easy. All the logs are in one place, all of your metrics, all your telemetry data. You have one application to debug. But one of the sacrifices, one of the trade-offs by splitting everything into modular and separate components is now we have a distributed system that we have to keep track of. Just for reference, some companies out there that are using microservice architectures today have published their service graphs that actually show the connections between all their microservices over the network. And we see some of these are 400, 500 plus microservices where one error in one place, one latency bottleneck can cause cascading issues, which of course we wanted to prevent, but the first part is observing it and diagnosing it. Just to give a reference, there's this tweet that we love at Solo. It goes, "We replaced our monolith with microservices so that every outage could be more like a murder mystery." Very cute. So let's dig into a little bit this dynamic. What are we actually dealing with in terms of architectural components? And we use this term service graph at Solo and in this talk in order to understand the actual map from service to service as they make requests out on the network to demonstrate the actual request flow as it exists. What composes our application? So we consider each service, each application, or each node, each service, each deployment as a node in this graph, and each route that connects them as an edge in the graph. So let's take a look at how in Kubernetes this is actually implemented in concrete terms. So in Kubernetes, I would deploy, let's talk about a single cluster. I would deploy a set of containers, each in their own pod or deployment. And in order to create a service graph between them, I'll use the services API of Kubernetes to create DNS names that the services can use to address each other. And this way I can orchestrate out a simple service graph within a single cluster. But what we're seeing is that this is not enough for customers in real use cases. In real production scenarios, you typically have multiple clusters that are running, and you even have those clusters are communicating out to environments that are running on hosted backends like EC2, or even cloud services that are external like S3. So we need a way now, if we really want to observe and parse and understand and grok this whole system, we need a centralized, unified way to do so. This can be done with application code, which we've seen in the past, and there are libraries that were sort of the predecessor to service mesh that exists today that were used to create a unified logging layer, unified metrics, configuration layers for routing. But now we see service mesh as the evolving solution in this space to provide that functionality. So let's look at what it actually looks like in a service mesh architecture. What does that actually look like in terms of components? So if you see in this diagram here, I have some applications. They're all communicating with each other directly through their sidecar proxies. Across clusters, those proxies are talking through ingresses. And again, those proxies handle routing into and out of the cluster itself to talk to external services. So we leverage the benefits of external service discovery, multi-cluster service discovery, and service identity that are provided by the mesh. Service identity allows us to trust that something that's outside of our cluster is actually the identity that it says it is, because it's secured with MTLS. But there are some challenges to this. This actually makes our microservice complexity problem even more challenging because we now have additional network hops, additional points of failure, and now multiple networks that we have to understand how to stitch together. So all of these represent pain points and an increased need for observability into our system, essentially, to understand what's going on. On top of that, we now have control planes that we have to configure. We may have shared control planes between multiple clusters. We may have a per cluster control plane approach, but the point is that there are a lot of moving parts going on. And this becomes increasingly difficult when we start to see errors come up. Those dreaded 503s. How do we understand the system? How do we trace problems back to their roots? Well, while we've enabled these complex architectures through the routing capabilities of a service mesh, we can now also debug them through the observability features of a service mesh. And those observability features, which we also refer to as telemetry, are actual data that we're scraping about all network transactions that are happening in our cluster, everywhere we have a proxy or in each cluster as well as in external environments. We have all of these proxies that are distributed everywhere, and they are observing what we tell them to. They're generating metrics, logs, and traces from all that traffic. And we'll do a little bit of an overview of what each of those is and their benefit to the system, how we can use these. So metrics are aggregated data about our service graph. They're telling us how the application as a whole is performing over time. We can see it broken down by cluster, by individual service, by services in namespaces, by services in their particular environment. This is extremely useful for telling when did performance issues begin, which metrics coincide. How can we tell, how can we get more of a high-level vision of what's happening with our system and respond to it in real time? The next step we'll discuss is logs. Logs give us more detailed information about each individual event. We can generate access logs for every single individual request and response that happens within a mesh, or we can filter it down to just what we want to observe. But what we get are detailed information, including request and response headers and metadata about bodies and so on, about every single request. This helps us to diagnose individual errors that occurred, as well as to know that requests are conforming to the protocols that we've established. So, for example, that headers are being specified correctly, that requests are being sent to the correct places, and essentially that the expected behavior is happening as we want. And finally, we have traces. When we see errors occurring and latency spikes occurring in our network, we want to understand the source of the problem. And we want to take these long request flows and break them down into their component pieces. And that's where traces help us out. Traces allow us to connect a series of individual events across the service graph into what's called a span, which essentially spans multiple request response flows that are a part of an individual workflow from the application point of view. This helps us identify where are the latency bottlenecks and where are the root causes of our errors in our system. So I'm going to hand it over to Eitan now to discuss how we can now take these observability primitives and bring them up a level for these advanced service graph architectures. Eitan?
Awesome. All right, thank you, Scott. Let's see that we are on. Cool. So as Scott mentioned, now we're going to talk about how we extend these observability primitives to multiple clusters to help us debug these complex service graphs. So again, as Scott mentioned, the service mesh provides telemetry data out of the box, which is incredibly useful for figuring out problems at the cluster level. However, it doesn't scale so perfectly to the multi-cluster scenario. And as we mentioned, these service graphs are growing quickly. And our customers are telling us this. And they're including other clusters. They're including external services. And customers want a way to view all of their data in one place through a single pane of glass, as we like to call it. And so the problem becomes, how do we collect and aggregate this telemetry data across multiple environments? So to illustrate this problem, we're going to start with a simple cluster scenario. So here we have Istio running in a single cluster environment. with just a couple of services, and Prometheus is deployed there. So Istio is creating metrics for all of these requests, and Prometheus is scraping them. And so the operator, the developers have access to these metrics so that they can figure out what is going on in the system. However, let's scale this up. Now, all of a sudden, we have multiple clusters, and each one of them with their own services, their own control planes, their own metrics, and their own Prometheus instances. So now, when in order to deduce what's going wrong in the system, potentially a bunch of different metric sources need to be checked to figure out what's going wrong. And this only becomes more complex as we add cross-cluster communication. So now, not only are we trying to grok or understand what's going on in individual clusters, multiple of them, but across clusters. And with these added network hops, it's just so many more data points. So this gets back to that single pane of glass, the ability to aggregate all of this data into one place so that users can actually access it and act on it. So the way that we like to describe the single pane of glass as a layer which aggregates all of our telemetry data into a single place. It adds context for cross-cluster and hybrid environment data and creates actionable, useful metrics to help prevent and or solve outages. And it's worth noting that this is, we see customers wanting this all the time, trying to get the best picture of the data possible. And now we're going to show a quick demo showing off what this single pane of glass observability gets us towards understanding our system better. Now, before we jump into the demo, just a little bit more context on what the demo is showing. Because as mentioned, these multi-cluster environments can be very complex. So in this case, we have two clusters. One we're going to call the management cluster, the other the remote. Important to note, you don't need to memorize everything that's in this picture. I'm going to go over it again, but I just wanted to give an idea of what's going on here. So each one has multiple services. It is similar for those of you who know the Book Info app. It is the Book Info app deployed, however, across multiple clusters. And again, I'll explain more as we go into that. So, and we have our single pane of glass running our observability aggregate. So let's go ahead and see some graphs. So here we have Grafana running. And for those of you who are familiar with Grafana, it's one of the most popular tools around for visualizing data, any kind of metrics. In this case specifically, it's visualizing Prometheus, but it can visualize others as well. And there are just a few simple graphs here just to demonstrate the power of this system. The first one up here, as it says, is the average 503 requests per 2 minutes, the average 200 requests per 5 minutes, and the request latency. So in order to demonstrate how this single pane of glass can help us deduce errors in our system, I'm going to manually inject some faults into our system. So as that's happening, I'm going to quickly show off where I've injected those faults so that we can see them reflected in the graph. So if we take a look at the faults that we've injected, our little chaos monkeys, we've injected some chaos monkeys and some latency. And as you can see here, for instance, when the reviews v3 service calls the ratings v1 service, it's going to introduce latency about 25% of the time. And when the product page calls the reviews v1 service, it's going to inject a 503 25% of the time. So again, no need to memorize, just trying to help visualize the service graph before we jump into the stats. So now, as you can see, this graph a minute ago was totally flat. But now we've got our 503s rolling in. And so and similarly down here for the request latency. So let's take a look at the labels that we have on our data, which can really help us understand and grok what's going on in the system. So let's take a look, for instance, at this final metric. As we can see, it says that the destination cluster is the remote cluster. The destination workload is our reviews v3. And our source cluster is the management cluster, and the source workload is the product page. So our two services are actually talking to each other across clusters, but we can see it as if it were just a normal network edge. So, and if we go ahead and look again at our picture, we see that we did introduce a chaos monkey into that communication. And we see that right here in our request latency. So that is actually this request latency is right here because the reviews calls the rating. So we see that right here in our graph. And if we go ahead and look at our 503s, we can also see that all of the places where reviews calls ratings across both of our clusters at the same time are represented in our graph. So this is just the beginnings of the power of multi-cluster observability with a single pane of glass. And now Scott's going to go over some of the problems and other ways that we have solved some of them.
Thank you, Eitan. So just to recap, what we've really just seen here, what Eitan just showed us, is that we're getting telemetry data of everything within all of our clusters as well as across our clusters. This is one of the benefits to having a single pane of glass that stretches across multiple clusters. Because in the end of the day, in the service graphs we're seeing users rolling out, the ones that they need are built across cluster. And so they're going to need that telemetry data to work not just within their own cluster to diagnose problems, but across clusters as well. So let's recap some of the reasons why we want this single pane of glass, what some of the challenges are when we get to these complex service graphs. So one, we have added network hops that all of the traffic has to flow through in order to make it across disparate environments. This can make it pretty complicated to understand what's going on. Additionally, we have to establish trust. Different environments have different sources of truth. On AWS, I may be using IAM roles for my pods. On GKE, I may be using GKE IAM. Those are two different trust domains. We need something in the middle that's going to be able to map them in order to permit those services to talk to each other. And additionally, we have configuration sprawl. There's a huge amount of configuration that winds up going into all of this, and it can be very hard to manage, especially when you're considering additionally orchestration and issues that are encountered during upgrades, because there are API changes that have to happen, and it becomes very complicated to manage all of this from a single place. And finally, we need our ability to observe and debug things that are happening, even though it's a distributed system. To us, it's still one single architecture. It's an application backend. It is a company software product that we really want to understand. So this single pane of glass provides solutions to this problem. It provides us high-level insights across our application infrastructure. It gives us a single point of access to view all of our data. And it gives us a unified abstraction for working with a mesh. But there are additional problems. What about traffic control? What about security? How do we manage those across clusters? How do we manage upgrade and install and tooling? We propose the concept of a management plane, another plane to add to your service mesh Kubernetes microservices infrastructure. So do we really need another plane? Well, we think so, and we think the customers are bringing us there. So let's explain. There, we've highlighted the pain points, the major points of moving to multi-cluster and multi-cloud deployments. We need a way to consolidate configuration of those environments in a way that is adaptable. And this management plane, it can really be anything. We've seen customers implementing simplistic versions of it through CI/CD workflows that are managed through GitOps, everything from that to custom controllers, open source solutions, and even proprietary solutions that are being sold by vendors today. But we all see that this ecosystem, the advanced front-running large enterprises are moving to these architectures. So we need a way to consolidate configuration, as well as to a way to aggregate all of these different environments into a single pane of glass to turn this murder mystery into a relaxing game of Clue. So just looking again at our architecture, understanding that we have lots of different complex communication going on. This is a challenge just for this pane of glass. But now we have the additional problem of wanting to solve configuration across clusters, as well as orchestrate workflows. For example, things like rotating certificates, deploying new services into our mesh, upgrading and rolling back new configurations and versions of infrastructure components. So finally, we have to put our shameless plug in here. Everything that you saw today was demoed with GlueMesh. GlueMesh is providing these features out of the box. We have open source that you can try that contains a ton of these features. And then there is an enterprise version that comes with support. We definitely advise checking it out. And really the purpose of this talk is not to shill GlueMesh as much as it is to shill a management plane. The understanding that trying to solve all of these problems at the control plane level gets out of hand very quickly. And we need a layer of abstraction here. We really feel that this is pushing in that direction. So yeah, and that's about it. We're Solo IO. We have a bunch of different tooling and products in the API space, gateways, ingress, service mesh, WebAssembly. We have a lot of projects there that are worth checking out. And also, if you're interested, if you're the type of person who's interested in IstioCon, you're probably interested in SoloCon too, which we're going to do more of a deep dive and get to explore some of these things with the community, with the customers, and that's March 23rd to the 25th. So that about wraps it up for us. Thank you, everybody. Really appreciate it.